Imagine a world where space and time could be in two places at once. A reality where the very fabric of our existence is not as rigid and singular as we once thought. It sounds like something out of science fiction, a concept that bends the very foundation of our understanding of the universe. But what if this idea isn't just a flight of fancy? What if it's a glimpse into the true nature of reality? Yet this is precisely the mind-boggling possibility that some physicists are beginning to explore. These scientists are pushing the boundaries of what we know, venturing into realms that challenge our deepest assumptions. This exploration takes us to the very edge of known physics, where the worlds of quantum mechanics and general relativity collide. It's a frontier where the smallest particles and the vastest cosmic structures intersect in ways we are only beginning to understand. Quantum mechanics, the theory governing the microscopic realm of atoms and particles, has revealed a universe steeped in uncertainty and superposition, where particles can exist in multiple states simultaneously. This principle of superposition is not just a theoretical curiosity, it has practical implications in technologies like quantum computing. General relativity, on the other hand, describes the large-scale structure of the universe, where gravity reigns supreme, warping the fabric of spacetime. This warping is what we perceive as gravity, a force that governs the motion of planets, stars, and galaxies. The challenge lies in reconciling these two seemingly disparate worlds. How can the smooth, continuous fabric of spacetime coexist with the granular, probabilistic nature of quantum mechanics? This question has puzzled scientists for decades. Can the smooth, continuous fabric of spacetime, as described by Einstein, accommodate the granular, probabilistic nature of quantum mechanics? This is not just a theoretical puzzle. It has profound implications for our understanding of the universe. This is where the concept of spacetime existing in multiple shapes, a superposition of configurations, arises. Imagine spacetime not as a single, unchanging entity, but as a dynamic, ever-shifting tapestry that can take on multiple forms simultaneously. It's a concept as perplexing as it is profound, potentially revolutionizing our understanding of the universe's very essence. If true, it could open up new avenues of research and technology, fundamentally altering our perception of reality itself. The journey to uncover these mysteries is just beginning, and the implications are as vast as the cosmos. Our journey begins with Albert Einstein and his groundbreaking theory of general relativity. Published in 1915, this theory revolutionized our understanding of gravity. Before Einstein, gravity was seen as a force acting between objects. Einstein, however, proposed a radical shift in perspective. He posited that gravity is not a force, but a consequence of the curvature of spacetime. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the trampoline's surface, causing nearby objects to roll toward it. Similarly, massive objects like stars and planets warp the fabric of spacetime around them. This warping is what we experience as gravity. Einstein's theory was a triumph, explaining anomalies in Mercury's orbit and predicting the bending of starlight around the sun. It painted a picture of a dynamic, interconnected universe where space and time are no longer static backdrops, but active participants in the cosmic dance. However, Einstein's universe, for all its elegance, was incomplete. It lacked the tools to describe the behavior of the universe at its smallest scales, where the rules of quantum mechanics hold sway. The problem of quantum gravity arises when we try to apply the principles of quantum mechanics to gravity. Quantum mechanics, developed in the early 20th century, describes the behavior of matter and energy at the atomic and subatomic levels.
One of its key principles is that energy and matter are not continuous but quantized, meaning they exist in discrete packets or quanta. Another central concept is wave-particle duality, where particles like electrons can exhibit both wave-like and particle-like behavior.
These quantum principles have been incredibly successful in explaining a wide range of phenomena, from the behavior of atoms and molecules to the interaction of light and matter. However, when applied to gravity, they lead to seemingly nonsensical predictions. Attempts to describe gravity as a quantum field, similar to the electromagnetic force, result in infinities and inconsistencies, suggesting a fundamental incompatibility between the two frameworks. This incompatibility lies at the heart of the quantum gravity problem. Section 4. Loop, Quantum Gravity, and String Theory, a tale of two theories. In the realm of theoretical physics, two prominent theories have emerged in the quest to unify the fundamental forces of nature: loop quantum gravity and string theory. These theories represent the cutting edge of our understanding of the universe, each offering a unique perspective on the nature of reality. Despite the challenges, physicists have not been deterred in their quest to unify gravity and quantum mechanics. The journey has been long and arduous, filled with countless hours of research, debate, and experimentation. Yet, the scientific community remains undeterred, driven by the tantalizing possibility of a unified theory that could explain the workings of the cosmos. This pursuit has led to the development of several promising theories, each attempting to bridge the gap between these two pillars of modern physics. Conferences and symposiums around the world have become the battlegrounds where these ideas are presented, scrutinized, and refined. The excitement in the air is palpable as scientists inch closer to a breakthrough.
Among the leading contenders are loop quantum gravity and string theory. These two theories have garnered significant attention and have sparked intense debates within the scientific community. Each theory offers a different approach to understanding the fundamental nature of the universe. Loop quantum gravity approaches the problem by suggesting that space-time itself is quantized. This means that, at the smallest scales, space and time are not continuous, but are made up of discrete units. This radical idea challenges our conventional understanding of the fabric of the universe. Imagine the fabric of space-time woven from tiny, interconnected loops. These loops form a complex, intricate network that defines the structure of the universe at the most fundamental level. The concept is akin to a woven fabric, where each thread represents a quantum of space and time. These loops, far smaller than the Planck length, represent the fundamental building blocks of space and time. The Planck length is an incredibly small scale, and these loops are even smaller, existing at the very limits of our current understanding of physics.
String theory, on the other hand, proposes that the universe is made up of tiny, vibrating strings. These strings are the fundamental constituents of all matter and energy. The vibrations of these strings determine the properties of the particles they form. Just as different vibrations on a violin string produce different musical notes, different vibrations of these fundamental strings give rise to the particles and forces we observe in nature. This elegant idea suggests that the diversity of particles and forces in the universe can be explained by the different ways these strings vibrate.
Both loop quantum gravity and string theory have the potential to provide a unified description of all the fundamental forces, including gravity. This unification is the holy grail of theoretical physics, promising to reveal the underlying simplicity of the universe. However, both theories are still under development, and experimental evidence to support either remains elusive. The search for empirical validation continues, with scientists devising new experiments and observations to test the predictions of these theories. The journey is far from over, but each step brings us closer to a deeper understanding of the cosmos.
Section 5. Probing the quantum fabric, experiments on the horizon. While a complete theory of quantum gravity remains elusive, physicists are not working in the dark. They are actively developing experiments and observations to test the predictions of these theories and gain further insights into the quantum nature of gravity. These efforts are not just confined to theoretical work, but extend to practical, hands-on experiments that push the boundaries of our current technological capabilities. The quest to understand quantum gravity involves a multifaceted approach, combining theoretical predictions with experimental validation.
One promising avenue of research involves searching for subtle quantum effects in the gravitational field. This involves looking for minute deviations and anomalies that could indicate the presence of quantum phenomena. Just as light can exhibit both wave-like and particle-like behavior, some theories predict that gravity may also display wave-like properties. This duality is a cornerstone of quantum mechanics and could provide a crucial link to understanding gravity at the quantum level. The idea that gravity could exhibit wave-like properties is not just theoretical. These gravitational waves, ripples in the fabric of spacetime, were first detected in 2015. This groundbreaking discovery opened up a new field of observational astronomy, allowing scientists to study cosmic events in a completely new way. However, detecting the quantum nature of these waves would require incredibly sensitive instruments capable of measuring fluctuations in spacetime on the order of the Planck scale. The Planck scale is incredibly small, making this a monumental challenge. Such instruments are currently beyond our technological reach, but researchers are continually working on developing new technologies that could one day make this possible. The development of these instruments involves cutting-edge technology and innovative engineering solutions, pushing the limits of what is currently possible.
Another approach involves studying the behavior of ultra-cold atoms in the presence of strong gravitational fields. By cooling atoms to near absolute zero and trapping them in carefully controlled environments, researchers can study the interplay between gravity and quantum mechanics with unprecedented precision. These ultra-cold atom experiments are incredibly delicate and require precise control over the experimental conditions. The atoms are cooled to temperatures just a fraction of a degree above absolute zero, where they exhibit quantum behaviors that are otherwise hidden at higher temperatures. Researchers use sophisticated equipment to manipulate and measure these atoms, allowing them to observe the effects of gravity on quantum systems in ways that were previously impossible.
These experiments, while challenging, hold the key to unlocking the secrets of quantum gravity and revealing the true nature of spacetime. The insights gained from these studies could revolutionize our understanding of the universe and lead to new technologies that harness the principles of quantum mechanics and gravity. The journey to uncover the mysteries of quantum gravity is a long and arduous one, but the potential rewards are immense. As scientists continue to push the boundaries of knowledge, each new discovery brings us one step closer to understanding the fundamental nature of reality.